A dam is like a traffic light for water. You might be wondering why I said that. Well, that's because it's exactly what it does. A dam's main function is to control the flow of water, and it can either speed up or slow down the flow depending on what's needed at that time. I gave that explanation because today we'll be going over how one of the largest concrete structures in history, the Hoover Dam, was built. Closer to the end of the video, we'll go over some of the biggest lessons from the Hoover Dam, so make sure to stick around for that. The Hoover Dam is a concrete arc gravity dam located in the United States. It borders Nevada and Arizona and encloses Lake Mead, the largest reservoir in the United States. The dam was constructed over 5 years by the Consortium 6 Companies Incorporated and was actually completed 2 years ahead of schedule. Since 1900, plans for a dam to control floods, provide irrigation water, and produce hydroelectric power were investigated. However, the actual construction started in 1931. Coincidentally, this was also during the Great Depression, which brought thousands of much-needed jobs to the struggling economy. Like we mentioned a bit earlier, the Hoover Dam is an arc gravity dam. So what does that mean? An arc gravity dam is a combination between an arc and gravity dam. Let's go over what each of these are. An arc dam is literally a dam that's arced. It's curved upstream such that the force of water is pushed against the arc. This causes the dam to compress, which actually increases its strength. It's important to note here that concrete is strong in compression and weak in tension. The gravity portion of the dam is a little less complicated. It simply uses the dam's own self-weight to resist forces. The combination of the arc and gravity designs contribute to the Hoover Dam's strength and optimizes the design. By using both an arc and gravity design, less internal fill can be used in the gravity portion of the dam. This leads to a more efficient design and ultimately cost savings. Initially, 4 diversion tunnels were dug out, 2 on the Arizona side and 2 on the Nevada side. These tunnels redirected the flow of water around the construction site before the cofferdams were introduced. Shortly after, upper and lower cofferdams were then set up on the site to protect workers from the Colorado River and more easily divert the river into the tunnels. Cofferdams are enclosures made in a body of water where water can be pumped out of the enclosed area. If you watched my video on how the Brooklyn Bridge was built, you might be wondering how a cofferdam is different from a caisson. The main difference is a cofferdam is a temporary structure that's removed after construction, while a caisson is a permanent structure. If you haven't seen the video, check out the card in the top right or link in the description. After the cofferdams were set up, the construction area was dry and the construction could safely begin. Given the water pressure was highest at the base of the dam, the foundation would have to be the strongest section. The base of the dam was designed for huge water pressures of up to 45,000 psi, and correspondingly, it was made of separate blocks called lifts. Similarly, the rest of the wall was built on top of the foundation as blocks stacked on top of each other, a lot like Lego blocks. You're probably wondering why they didn't just cast the dam in one pour, which sounds a lot easier than building a bunch of Legos. This was mainly due to one thing: heat. When Portland cement undergoes hydration, heat is produced in a process called heat of hydration. As we can see from this graph, a significant amount of heat is generated when cement is mixed with water, and this gradually decreases as time goes on. In thick casts of concrete, there are natural temperature differentials between the inside and outside as it cures. The problem is that some of the areas of concrete will be expanding rapidly while others not so much. This ultimately causes tensile stress that will lead to thermal cracks if the tensile resistance of the concrete is exceeded. Essentially, to avoid thermal cracking, the Hoover Dam was casted in smaller blocks instead of one large wall. However, this alone wasn't enough. The wall also used cooling pipes in the concrete, where ice and water were pumped to lower the temperature of the concrete. These pipes were later filled with grout to accommodate any losses in strength. Over the 5 years of the Hoover Dam's construction, 4,360,000 cubic yards of concrete were used, which is enough concrete to pave a highway from San Francisco to New York City. By 1936, the Hoover Dam was complete, and there are 3 key lessons we can learn from it. The first lesson is that dam construction isn't as simple as building a wall and calling it a day. There are also many tunnels and other infrastructure behind the scenes that control the water flow and enable it to generate power. The second lesson is that extreme care must be taken when casting large pieces of concrete to avoid thermal cracking. Lastly, the successful operation of the Hoover Dam since the 1930s is really a testament to the reliability and practicality of hydroelectric generation. The Hoover Dam has been controlling floods and generating clean energy for generations. About 1 million people visit the dam each year to marvel at a historic piece of American history. This video was inspired by one of our viewers. Be sure to drop a comment below on the sort of videos you'd like to see next. Thanks for watching. Let me know if you enjoyed the video by smashing the like button, and remember to subscribe for more videos simplifying construction.